All right, so let's talk about the pH dependency of salts again. So one of the reasons it's hard is that you usually have some kind of competing equilibrium. And so here's my first one. Here I have calcium carbonate, and this is the thing that is generally found in shells. So it's a major component of shells. Shells obviously are found in the ocean. They house a variety of ocean life, etc. So they're relatively important. It's also relatively insoluble. It's got a KSP of about 10 to the minus 9. And so this equilibrium is highly favored towards the solid. The second equilibrium that we'll have to consider is the one between the carbonate, which happens to come from the calcium carbonate, and a proton that can come up in solution. So here we have a base, here we have a conjugate acid. We'll talk more about both of those in just a second. So let's go back to this. Okay, so these are the two equilibria we have. Ooh, look, equilibria. Those are our puzzle pieces. Okay, channeling my kindergartner teacher here. It's great. So, solid, mostly insoluble, mostly going to remain a solid. But because it is a solid, we have ions that interact with one another, and those ions stick together in a perfect crystal lattice, which obviously is not what I have here, but they're kind of perfectly locked in one orientation. Not what I have here, which I know, but that's okay, right? So here's what an ionic solid is. A bunch of ions interacting with each other. If it's even a little soluble, some of those ions are going to go off into solution, and that solution happens to be aqueous, right? So there's my aqueous solution of water molecules there, because those water molecules are helping to solvate these ions, and that's what puts them in solution. We'll go ahead and turn them right on up. Okay. Now this isn't going to happen that much because again the KSP is 1 times 10 to the minus 9, and so most of my ionic solid's going to stay in the crystal lattice form, and not much of it's going to form ions as it dissolves, but some of it will. Since some of it will, now I have a competing equilibria to deal with. Not for the calcium though. The calcium happens to be the conjugate acid of a strong species, so something like calcium hydroxide. And if this calcium interacts with this water and picks up a hydroxide ion, that's okay because we consider this a strong base and we consider that it's going to dissociate, and so it's just going to fall apart again. And so this guy here doesn't have a competing equilibrium because it's the conjugate of a strong species, just like we saw in the Bronsted-Lowry initial conversation about conjugates. This guy, on the other hand, is the conjugate base of a weak acid. And so it actually probably would rather be in the acidic form. And so these two minus signs are going to do a really good job of having their own equilibrium. So these two negatively charged oxygens, and remember that there's resonance within this, and so really it's 3 kind of equal bonds, but the minus signs help to illustrate my point better. So if you're wondering, is there resonance there? Yes, I'm just ignoring it right now for my benefit. Okay, so what happens is I had a solid, my solid put an ion or so into solution, and now if I happen to have a proton, and here's my proton, and this is the simplified form of it because it was nice and easy to make. Remember that it's probably coming from H3O plus though. Okay, so here's my H3O plus, but I'm just gonna have the ion. Now here's my proton. I added some water or some acid to my water, and now I have an acidic solution. That proton from the acidic solution comes and interacts with this actual ion from my conjugate base equilibrium and starts to form this second equilibrium. Okay? Same conjugate base, same carbonate anion. Now what happens over here is that I have to fill this hole. And the only way that my salt can fill the hole is by dissolving more of the calcium carbonate. And so while before I had a collection of 3 little ions over here, Now I only have a collection of 2 little ions. I've increased the solubility because I had to shift some of these ions to the product side in order to fill this hole that was formed as this carbonate anion went over here to this second equilibrium where the proton and the carbonate make the conjugate acid of this conjugate base. Now, given the K values or the equilibrium values, this is probably more favored than that. And so we don't want our oceans acidic, because every time I have a proton, right, this isn't going to happen once. This is going to happen every time I have a proton. I'm going to pull something out of that original equilibrium. I'm going to form some of this conjugate acid, which means that some of my shell has to go ahead and dissolve even further. And so that's not great because we like having shells in the ocean. So pH dependency of a weak conjugate in solution is actually a really important concept. Not one you'll have to do calculations on, but one you'll have to be able to explain in terms such as this.